Good morning, everyone. Thank you for joining today's class. So I will be going to talk about non-Newtonian fluid from subchapter 3.5. So this will be the last subchapter in chapter 3 that we will discuss. And don't forget that next Monday we will have a quiz that starts at 8:50 a.m. sharp, offline. So we will meet in class. And don't forget also to submit your assignment, a previous assignment. And yeah, please be prepared. Okay, so I'm going to explain to you about the last subchapter in chapter 3. Okay, so before we going deeper into non-Newtonian fluid, I will talk about how the Newtonian fluid and non-Newtonian fluid differ. Okay, so for Newtonian fluid, yeah, of course, it will follow the Newton's law, yeah, where the viscosity is only a function of temperature and pressure and is independent to shear rate, yeah. While for non-Newtonian fluid, yeah, as mentioned in the title, yeah, non-Newtonian fluid, so it does not follow the Newton's law, yeah. So the viscosity does not only change because of the temperature and pressure, but it also changes, yeah, because of the shear rate and the force acting upon it. Okay, now therefore, yeah, for Newtonian fluid, yeah, since it's independent to shear rate, yeah, now the shear rate increases linearly along with the shear stress. Yeah, that's why you can see here that Newtonian fluid, yeah, has a linear line, while for non-Newtonian fluid, yeah, one of the requirement, yeah, is the shear rate does not increase linearly along with the shear stress. That's why when you see these two lines, pseudoplastic and dilatant, yeah, you can see that the shear rate does not increase linearly, yeah, along with the shear stress. Now, another requirement for non-Newtonian fluid is that the non-Newtonian fluid, yeah, usually requires initial shear stress to initiate flow, while Newtonian fluid don't. Yeah, that's why when you see Newtonian fluid line here, yeah, it starts from the origin point, yeah, or tau equal to 0. Yeah, why? Because Newtonian fluid does not require shear stress to initiate flow. Meanwhile, for non-Newtonian fluid, yeah, another requirement is that non-Newtonian fluid requires initial shear stress to initiate flow. Yeah, that's why Bingham plastic fluid here, yeah, is also considered as one of the non-Newtonian fluid. Why? Because even though, yeah, it has a linear line, yeah, which means the shear rate increases linearly along with the shear stress, but yeah, Bingham plastic fluid requires initial stress or tau O, initiate flow. That's why it's considered as a fluid. Yeah. Now, non-Newtonian fluid itself can be divided into two big groups: time dependent and time independent fluid. Okay, time dependent, yeah, means that these types of fluid dependent to both shear stress and duration of the shear. Yeah. Meanwhile, for time independent, yeah, it's only dependent only to shear stress applied, but not to the duration of the shear. Okay, yeah, so we will abbreviate it, yeah, to TD fluid, TDF, and TI fluid or TIF. Okay, so we go to the TIF first. Yeah, so there are three types of TIF. Yeah, first is Bingham plastic fluid. So it is a viscoplastic material. Yeah, so it's a fluid that behaves as a rigid body at low stress, but flows as viscous liquid at high stress. So when there is no stress, yeah, it behaves like a solid. But during yeah, when the shear stress is applied, yeah, it will flow as a viscous fluid. Okay? Yeah. Shear stress and shear rate, yeah, correlate linearly. Yeah, similar to Newtonian fluid, right? That's why it's linear. Yeah, here for Bingham. But it requires initial shear stress, yeah, or initial tau O flow. Yeah. Yeah. Several examples, yeah. Toothpaste, margarine, chocolate mixture, soap, grease, drilling mud, yeah. So if you imagine toothpaste, yeah, when we do not give it a squeeze, yeah, it will behave like a solid. It will not flow anywhere, right? For toothpaste, yeah. If we did not do anything to toothpaste, yeah, it will not flow, right? It will just stay there, yeah, as a toothpaste, yeah. But when we squeeze, yeah, when we give the toothpaste a squeeze, yeah, we give the toothpaste tube a squeeze, then the toothpaste starts to flow. It start coming out from the tube, right? Yeah, yeah. It goes as well for the others. Yeah. Okay. Now, the second type of TIF is pseudoplastic fluid. Yeah, or shear thinning fluid. Yeah. Now, this type of fluid, yeah, decreases its apparent viscosity when the force or shear stress is applied. Yeah, so when the shear stress is applied, yeah, the apparent viscosity get lesser and lesser. Yeah. Yeah, now the flow curve, yeah, can be seen here. So this is pseudoplastic. Yeah. Yeah. And it can be also represented by this equation. Yeah. Yeah. So the correlation between the shear rate and then the shear stress, yeah, can be correlated using this equation too. Yeah. With n less than 1. Yeah. Now n is the flow behavior index. Yeah. Okay, now okay, the apparent viscosity, or we can say it's the viscosity when certain shear stress is applied, yeah, it can be calculated using this equation, yeah, equation 3. Okay, so this is the apparent viscosity. So mu A is apparent viscosity, or viscosity when a certain shear stress is applied. Yeah, now the example of the shear thinning fluid is polymer melts. Yeah, detergent slurries, mayonnaise. Yeah, so you can imagine when we open up a new mayonnaise, yeah, it will be very viscous. Yeah, but once we stir it, we give it stress, we apply the shear stress, yeah. We stir it for like 5 minutes, it starts to become less and less viscous. Yeah, it starts to be thinner, yeah, not thicker. Okay, yeah, so this one of the example of the pseudoplastic fluid or shear thinning fluid. Okay, now we have another one we call as dilatant fluids or shear thickening fluid. Yeah. Okay, so yeah, it has n higher than 1. Yeah. So for shear thinning fluid, the n or the flow behavior index is less than 1. But for the vice versa, the shear thickening fluid, yeah, the n is higher than 1. Yeah. So in contrast to pseudoplastics, yeah, this dilatant fluid increases its apparent viscosity when the force or shear stress is applied. So when you stir it, yeah, when you stir it, let's say for 5 minutes, it's not getting less and less viscose. No, it's getting more and more viscose. Yeah. for example, is cornstarch suspension. Yeah, so it actually behaves like a liquid at low stress. Yeah, but it will solidify, yeah, when the force is applied. That's why sometimes people can run, yeah, on it. Yeah, I don't know whether you have seen a variety show in Japan. Yeah, they sometimes have. Oh, sorry. Okay. Now, they sometimes have a game where people start to run, yeah, on the cornstarch suspension. Yeah, when they run, they can stay above the liquid, but once they stop running, yeah, they will start to sink. Yeah, yeah. So that's the latent fluids. Yeah. Now the flow curve again, you can see in the figure 3.5-1. Yeah, and the profile. Yeah, the shear stress versus shear rate profile. Yeah, is expressed by this equation 4. Yeah. So these are another example of the latent fluids with wet bit sands, potassium silicate in water, or other solution or other suspension with high concentrations of powder. Nah, nah. Okay, so after TIF, we will go to TDF. Yeah. So there are two types of TDF. Yeah. First is thixotropic. Yeah. So it's time-dependent shear thinning fluid. So it's similar to pseudoplastic, yeah, because it's shear thinning fluid. However, yeah, since it's TDF, yeah, since it's TDF, yeah, so the viscosity of the fluid of this type of thixotropic fluids, yeah, it will getting less and less viscous by the time as well. So it's not only depending on the shear stress applied, but it also depending on the time. Yeah. Now, okay, the longer the fluid undergoes shear stress, the lower the viscosity. Yeah. Okay. However, after it undergoes stress, yeah, and then you keep it, yeah, the thixotropic fluid will return back, yeah, to a viscous fluid, yeah, after a certain time. Yeah. Example: shortening, ketchup, or yogurt. Yeah. So let's say for yogurt, yeah, when you eat first, yeah, when you eat at first, yeah, it will be, it will behave like a solid usually, yeah. However, when you stir it for quite sometimes, yeah, it will start to get less viscous and less viscous. Yeah. However, once you put it again, put it back, and then just leave it, yeah, without giving it any more stress. Yeah, just leave it, and then tomorrow you eat again. Yeah, the texture will come back. It will again behave like a solid. Okay. Yeah, that's thixotropic fluid. Yeah. And then the second one is rheopectic fluid. Yeah. It's a rare type of fluid. Yeah. In contrast to thixotropic fluid, yeah, the longer the fluid undergoes shear stress, the higher its viscosity. Yeah, it's just like lubricants. Yeah, so this is actually the same like the latent fluid. Yeah, but it's the TDF version of it. Yeah. So the example is lubricants, gypsum paste, printer ink. So if you have ever tried to play with the printer ink, yeah, at first it's not viscose. Yeah, usually it's not viscose, but when you apply stress, when you stir it, yeah, it will start to behave like a solid. Yeah, because getting higher in viscosity. Yeah. Okay, and then we actually know another type of non-Newtonian fluid, yeah. We call it as viscoelastic fluid. Yeah, which exhibits elastic behavior. So it's like rubber. Yeah. So it exhibits elastic recovery, yeah, from deformation upon the removal of the stress. Yeah. So typical example is the dough. Yeah. So if you want to make a loaf of bread, if you make a cake, yeah, you will knead the dough, right? Now, when you knead the dough, yeah, its shapes will be deformed. However, it will always elastically recover to its original shape. Yeah, that's why sometimes if you see any cooking video, any baking video, sometimes they will just knead and then punch, yeah, the dough, right? But after that, it will just come back to its original shape. Yeah. Yeah, so another example is napalms, is bitumen. Yeah, okay. However, yeah, since the theory for the TDF has not been fully developed, yeah, so in this subchapter, we will only talk about TIF, type, yeah, of non-Newtonian. Okay, okay. So, yeah, after we know about the TIF, about the TDF, about non-Newtonian fluid in general, then we will go to talk about how this type of fluid flows inside a pipe. Yeah. So we will go again, yeah, to laminar and turbulent flows. Yeah, we will hear these terms again. Yeah. Okay, so for laminar flow of TIF, yeah, for TIF flowing in a tube, yeah, it will follow the equation of 3.5 S5. Yeah, or we call it as a power law equation. Yeah. Yeah, so for teeth flowing in a tube, yeah, it will follow this law, this power law. Yeah, so tau W, yeah, equals to diameter of the pipe times delta pressure of the pipe. Yeah, delta pressure of the fluid inside the pipe, I mean, divided by 4 times the length of the pipe, equals to K exon times 8 phi, yeah, 8 times velocity divided by D of the pipe, yeah, to the power of n exon. Yeah. Okay. Now, the general flow curve of TIF in a tube, yeah, can be seen in this figure. Yeah. So this is actually the shear stress at the wall. This one is the shear rate, yeah, at the wall. Yeah. Okay. So the shear rate of the wall, yeah, the shear rate of the wall is actually can be expressed as this equation, as in this equation. Yeah. This is the shear rate at the wall. Yeah. Since this one is a constant, so that's why I can say that the shear rate at the wall, yeah, is proportional to 8 phi over d. Yeah, that's why it's 8 phi over d. Yeah, here in the graph. Now, okay, so maybe you question this, yeah? What is this n axon or k axon? Yeah. Okay, so n axon, yeah, is the slope of the line in this figure, yeah? This n axon is actually the flow behavior index. Yeah, so n axon equal to 1 if it's Newtonian. N axon is less than 1 if it's pseudo-fluid or Bingham plastic curve. N axon is higher than 1 if it's dilated. Yeah, so n axon is equal to n. Yeah, before above, yeah, in the previous slide, yeah, we talked about n, right? Yeah, it's flow behavior index, so it's the same, n axon. And what is this k axon? Yeah, so k axon is consistency index of the fluid. Yeah, or I can say that k axon is the Newtonian the viscosity in Newtonian fluid. Yeah, it's viscosity in Newtonian fluid. Yeah. Okay. Okay. Nah. Okay. Nah. For non-Newtonian fluid, yeah, the value of k axon and n axon, yeah, yeah, is actually found to be constant, yeah, over the range of the shear stress. Yeah. So by experiment, yeah, many researchers found that the value of Kxn and Nxn is constant over the range of shear stress. Yeah, even though for some liquid, this is not the case. Yeah, however, in most of the case, yeah, this Kxn and Nxn, yeah, is constant over the value of shear stress. Nah, okay. So that's why in this class, yeah, we will regard these two components as constant. Yeah, nah. And then how do we know the value of this Kxn and Nxn? Yeah, we can see table 3.5-1. Yeah, so we go down. I will show you the table. Yeah, this one. Okay. Yeah, so for 14.3% clay in water, then we will have Nxn equals to 0.350. And K, yeah, oh, we don't know. We don't know the value of K. Yeah, we don't know the value of K. Yeah, here. Now, how to find the value of K? Yeah. Now later we will talk about the correlation between the Nxn and N, K and Kxn, and then gamma and Nxn and K. Yeah, because these three values will correlate to each other. Okay. Nah, okay. Now, the correlation between N and Nxn, yeah, can be seen in equation 7, K and Kxn in equation 8. Okay, so I will go up or down. Or go up then. Here. Yeah. So as I said previously, Nxn and N are equal to each other. Yeah, so this is correlation between N and its Nxn counterpart. And then this, yeah, it's Kxn equals to K times blah, blah, blah. Okay, yeah. So if in this table it's K, right? It's not Kxn, but you need Kxn actually in the in the in the equation in equation 5, yeah. You need Kxn. Then you can use this equation, yeah. So you put the value of K here. You know the value of Nxn from the table as well. Then you will know the value of Kxn. Miss, I don't know the value of K because it's empty. How do we get the value of Kxn then? Nah, we can use this. We can use equation 9. Yeah, now the correlation between Kxn and Nxn is shown in equation 9. Yeah, so this gamma is actually the generalized viscosity coefficient. Yeah, so if you don't know the Kxn value, but you know the gamma and the Nxn value, then you can find the Kxn value. Okay, nah, and then the conversion factor for gamma from SI unit to English unit, yeah, can be seen here. Sorry, can be seen here. So if the problem, yeah, it's in the English unit, yeah, but what you know, yeah, from this table, it's SI unit, right? It's SI unit. But the question is in uh, English unit, yeah, then you can use this correlation, yeah, this conversion factor, yeah, to change the gamma value from SI unit to English unit. Nah, okay, yeah. Similarly to what we've learned in chapter 2, yeah, a flow in a pipe, yeah, for Newtonian fluid, they have the delta P. It goes as well in the uh, non-Newtonian fluid. Yeah, they will also have delta P. Yeah, now to obtain this frictional pressure drop, yeah, or pressure drop caused by friction, yeah, you may use equation 10 or equation 50. Equation 10 or equation 15. Later we will discuss about it. Yeah. Lumis, how do we know when we will use equation 10 and when we will use equation 15. Yeah, it depends on the known variables in the problem. Yeah, so if the problems give you all value of this, then you can use this equation. If the problems give you another terms, yeah, or another parameters, then you may have to use the equation 15. So it depends on the variables known in the problems. Okay. Now, and then yeah, in chapter 2 we also try to find out the average velocity, right, in the pipe. Yeah, average velocity of the fluid in the pipe. Yeah. For TIF or for non-Newtonian fluid inside a pipe, sometimes we also need to find the average velocity. Yeah, we can use this equation. The diameter of the pipe, the delta P of the fluid inside the pipe, the length of the pipe, and then the K action and N action of the fluid. Yeah. Nah, but this use N action and K action, right? Now, how about if we want to use the N and K value, not K action and N action? Then we can use equation 12. Yeah, this is N and K. Okay. Now, oh, since we are talking about flow in pipe, so there will be a Reynolds number as well. Yeah. So this is the generalized Reynolds number. Yeah, generalized Reynolds number. How to calculate? Use this. Yeah. The laminar flow, yeah, has a Reynolds number, has a generalized Reynolds number of less than 2,100. Yeah. Yeah, so, oh, Miss, I want to use gamma and N action. Yeah, then use this, yeah, to find generalized Reynolds number. Miss, I want to use K action and N action. Use this. I want to use K and N. Use this. Okay? All will give you the same number of generalized Reynolds number. Okay, now, yeah. And then, yeah, I want to know the delta P here. I want to know the pressure drop in the pipe of the non-Newtonian fluid. Yeah, but I don't want to use equation 10 or 15. Oh, sorry, I don't want to use the equation above this. Yeah, above this sub-chapter. Yeah. Okay, then you can use the Fanning friction factor. Yeah. You can use the Fanning friction factor. Yeah. Yeah. This Fanning friction factor will be used in this equation of 15. Yeah. So if you still remember, it's similar to what we've learned in chapter 2. Yeah. Okay, yeah. So the Fanning friction factor, yeah, the F, small f, yeah, yeah, can be found, yeah, using this equation of 15. So once we know the generalized NRE, then we can put it here, then we can know the Fanning friction factor. Then this Fanning friction factor can be used to calculate the pressure drop using equation 15. Yeah. So that's why, yeah, depending on what you know from the problem, then you can use equation 10 or equation 15 to find the delta P inside the pipe. Okay, now, this is one additional note, similar again to chapter 2. Yeah, I hope you still remember. Please do remember it. Yeah, the friction loss, or FF, it's equal actually to delta PF. Yeah, over density of the fluid. Okay. Okay, so we go to see example 3.5 as well. Okay, yeah, we have a power law fluid having a density of this, flowing through a tube with this diameter. Oh, sorry, with this length and the diameter at an average velocity of this. So this is the V. This is the D. This is L. This is density. And then the flow properties of the fluid. are this. Yeah? We know the Kxn and Mxn. And then we are asked to calculate the pressure drop and friction loss using equation 10 for laminar flow. Yeah, so we use equation 10, yeah, for laminar flow, and then we are asked to check whether the Reynolds number shows that it is indeed the laminar flow. Yeah, so I use equation 10 here. Yeah, I know the Kxn, Nxn, V, D, and L. So we put all of that, then we get this 45,000 something. This is the delta P, and then and FF, or friction loss, yeah, is delta P over density, yeah, as I said previously here. Okay, so I divide the delta P with density, I know the FF. Yeah. Okay, and then after that, I want to use this value to check whether it's really laminar or not. Then I will use equation 13 to calculate generalized NRE. Yeah, I use the Nxn and Kxn version of equation. Yeah, so I put all the known value here. I get this. Oh yeah, it's indeed less than 2000 and 2100. So it's indeed laminar. Yeah. Now and then for B, yeah, I'll go up again. Yeah, repeat part A, but using the friction factor method. So I will use equation 15. Since it is really laminar, then I can use the equation 14 to calculate the bending friction factor. F equals to 16 over NRE gen. I get this. And then I substitute this value to equation 15. Yeah, 4 times F is 14.44. And I put all the known value here, and I get it's 45.39 km per square meter. So it's the same. Yeah, exactly the same as this. Okay. Okay, now. Okay, yeah. Since we are talking about flow inside a pipe, yeah. So aside from friction loss in a straight tube, yeah, friction loss can be also coming, yeah, by the contraction, the expansion, and fittings. Yeah. So for friction loss caused by fittings, yeah, use equation 17 from chapter 2. Yeah, 2.10-17, and use table 2.10-1. See? Yeah, so please do not forget what you've learned from chapter 2. Yeah. And then for friction loss caused by contraction. Yeah. Yeah, again, use equation from chapter 2. Yeah, that can be used for laminar flow. Nah, but usually, yeah, in this equations, yeah, it requires the alpha value. Yeah. The alpha value is 1/2, right, for laminar flow. Yeah, in Newtonian fluid. But this is not Newtonian fluid. This is a non-Newtonian fluid. So, yeah, we will calculate the alpha value using this using this equation. Yeah. Yeah. Okay. So when we want to use the equation of 16 from chapter 2, yeah, the alpha is not half for laminar flow. It's for Newtonian fluid. For non-Newtonian fluid, you have to use this equation to calculate its own alpha. Okay, after you know this alpha, then you put this alpha into the equation 16 of chapter 2. Okay, now, and then for friction loss caused by expansion, yeah, caused by expansion, yeah, then you can use this equation of 18. Okay. Nah, okay. So if you have any question, yeah, you can just drop a message in my WhatsApp or drop a message in the comment section of the YouTube video. or you can just directly ask me when we meet in the class. Yeah. Okay, so I will continue with turbulent flow. Yeah. Again, it is similar to what we've learned in chapter 2. Yeah. So for turbulent flow of TIFF, yeah, the correlation between fanning friction factor and NRE gen, yeah, with different n axon, yeah, can be seen in figure 3. So this is the laminar area. This is the turbulent area. Yeah, with different n axon. Yeah. This is the correlation between NRE gen with the fanning friction factor, and then again you will use the fanning friction factor to calculate the delta P in turbulent flow. Remember, remember that this figure is only applicable when this non-Newtonian fluid flows inside a smooth tubes. So if it's not a smooth tubes, then we cannot use this figure. Yeah, I will give you a new figure. Yeah. Okay, so this figure can be used only for smooth tube. Yeah. If there is roughness inside, yeah, then I will give you another figure. Okay. Okay, yeah. So this is an emphasize. Yeah, I emphasize here that from the figure we can see that the correlation between F and NRE gen is linear in laminar flow. Yeah, as in expressed in equations 14. Yeah. Nah, please do remember, yeah, this is an important note. Yeah, for pipe with roughness, so not the smooth tube, it is recommended to find F using using figure 2.10-3. Yeah, but the NRE, yeah, you have to change the NRE with NRE gen. So you can use the figure 3 from chapter 2. Yeah. But the NRE is calculated using the equation of NRE gen, not the common NRE. Okay, then you can find F, yeah, for pipe using roughness. Okay. Yeah, so you will go back and forth, yeah, from chapter 2 and chapter 3, yeah, for this type of calculation. Okay, now to obtain the pressure drop in straight pipe of turbulent flow of TIFF, yeah, you can use equation 15, friends. Wait a minute, where is 15? Up, 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 up. Here. So the same as the one in laminar, yeah. If you use friction fanning factor, then you can use the same delta P equation, yeah, to find the pressure drop. Yeah. Now the F value, yeah, you can find it using figure 3 in chapter 3 or figure 3 in chapter 2. Yeah. So using these two figures, yeah. For smooth tube, use this. For pipe with roughness, use this. But the NRE, yeah, shall be calculated using NRE gen equation. Okay. Again, yeah, additional information. Yeah, friction loss, yeah, equals to delta PF over density. Okay. Yeah, nah. Again, similar, yeah, to laminar flow. Yeah, aside from friction loss in the straight tube, yeah, friction loss can be also caused by the contraction, expansion, and fittings. Yeah. Now, for friction loss caused by fittings in turbulent flow, use equation 17 from chapter 2 and table 1 from chapter 2. Yeah. For friction loss caused by contraction, yeah, use equations 16, yeah, alpha equals to 1. Oh, so for turbulent flow, either TIF or Newtonian flow, the alpha is still 1. For laminar flow, the alpha is not half for non-Newtonian fluid. You have to calculate it. Yeah. And then for friction loss caused by expansion, yeah, then you can use equation 15 from chapter 2 with alpha equals to 1. Okay. Okay, so we go to example 2. Let me see. Yeah. Yeah. Okay, we have a pseudoplastic fluid follows the power law, having a density of this, flowing through a smooth circular tube. Okay, so I can use the figure above, yeah, 3.5-3. Yeah, with this diameter and then the velocity of 6.1. The flow properties are this, yeah, and then the length of the tube is 30.5 meters. Yeah. So actually, since this is turbulent flow, yeah, actually I don't know whether it's turbulent or not, so I have to check the generalized NRE first. Yeah. Oh, so it's 13,280. So it's definitely a turbulent flow. Yeah, so after I put all the known value from the problem, I know that the generalized NRE is this. So flow is turbulent. So the question is calculate the frictional pressure drop, so delta P. Yeah. So what I have to do is finding the F value, yeah, defining friction factor. So I will use figure 3.5-3. I will go up, yeah, and then the n action is 0.3. Okay, so I will go up, yeah. Okay, so n action is 0.3. Also, it's this line, this dash line, yeah. And then the NRE gen is 1.3 times 10 to the power of 4. So it's somewhere here. Yeah. So you just draw a vertical line up until it crosses the line of n action equals to 0.3. So it will give you a point here, right? And after that, draw a horizontal line up until it crosses the y-axis. Then you can get the F value. Oh, miss, if the n action is 0.5, so you have to draw an imaginary line here in between 0.4 and 0.6. Yeah. If the n action is not mentioned in this figure, then you have to do what you have to do is drawing an invisible, yeah, the imaginary line here. Okay. Okay, so I will go down again, yeah, and I know that the F value is 0.0032. So put it back to the equation of 15, yeah, put all the known value, then you can get delta P is this. Okay. Nah. Okay, yeah. Similarly, yeah, to what we've learned again in chapter 2, yeah, about the velocity profile for Newtonian fluid, we will also talk about velocity profile for pseudoplastic and dilatant fluid. Okay, now, so the velocity profile of these two type fluid, yeah, in a tube or in a pipe, yeah, is a function of pipe radius. Yeah, where near the wall, yeah, the velocity is 0, yeah, because of the friction. While in the center, the velocity is maximum. Yeah. Sorry. Nah. Okay. The shear stress, yeah, of these two type of fluid, yeah, in pipe, yeah, it it will start. It will. Oh, sorry. Yeah, it is expressed as in equation 19. Yeah. Yeah. So this is the shear stress, yeah, of TIF in pipe. Yeah. Yeah. Minus dvx, yeah, because it flows in x direction, and then the velocity changes, yeah, based on the radius. Yeah. So that's why the shear stress actually is a function, yeah, of a fluid, yeah, of a velocity of the fluid to its own radius, yeah, to its radius in pipe, yeah. Now, and then, yeah, using this equation from chapter 2, yeah, we can get, yeah, an equation, yeah, to calculate, yeah, the velocity at certain radius, yeah. Vx, yeah, Vx is a velocity at certain radius. Yeah. Oh, I want to know a velocity at this at this r. Then you can use these two equations. Yeah. Now, and then we will also know the average velocity, yeah, by using these two equations. Yeah. 12, yeah, and 20. Okay. So it's actually similar to what we've learned in chapter 2. Yeah. However, they use a lot of m and k, yeah, here. Yeah, they use a lot of constants, yeah, from the fluid. So that's why it looks more complicated, the equation, I mean. Yeah. Now, okay. Now, the correlation, yeah, between the velocity at certain radius and average velocity, yeah, can be seen here, yeah, or it can be seen here. Yeah. Okay. It can be seen here, or it can be seen here. Yeah. The correlation between velocity at certain radius and velocity average can be seen here or here. Okay, for different value of n. Yeah, this is n less than 1, so it's for sure thinning fluid. This is n more than 1, so it's for shear thickening fluid. For dilatant, this is for pseudoplastic. Yeah. Okay. Okay, so we go to see the next subchapter. Nah, for Bingham plastic fluid. Nah. Nah, for Bingham fluid, yeah, similar derivation, yeah, is also performed, yeah, for Bingham fluid, yeah. So because previously what we talked is about and sorry, it's for pseudoplastic and dilatant fluid, right? But we have not talked about the Bingham fluid. So for Bingham fluid, yeah, a similar derivation is also done, yeah, for this type of fluid. Yeah, however, the shear stress, yeah, for Bingham is expressed as this. Yeah, so if previously Trx equals to mu times minus dvx per dr, yeah, but for Bingham fluid, I will add with tau O, because, yeah, for Bingham plastic fluid to flow, it requires this tau O, this initial shear stress. Okay. Yeah. Okay, so I hope that you still remember this concept from the early part of this class. Yeah. Nah, okay. Miss, where do we get the value of tau 0? Because it's actually constant, right? Yeah, nah. Several tau 0, yeah, several tau O, yeah, required for several types of Bingham fluid, yeah, can be seen in table 2. So I will go down. Okay, here. Yeah. Okay, this is the tau O. Yeah, for coal slurry, for molten chocolate, for printing pigment in vernice. I know that the tau O is this. Yeah. So if I have another type of fluid mist, yeah, then it will be known in the problem. Okay. Yeah. Okay. So for Bingham plastic fluid, yeah, it will have a velocity profile inside a pipe like this. So 0 near the wall, and the highest is exactly in the center. Yeah, however, If previously it like an ellipse, right? But this one, no. Yeah. It has a blunt, or maybe I can say it has yeah, I think a blunt, yeah. A blunt area here, a plateau area here, yeah, for the velocity. Yeah. So when you see here from r equal to 0, is here, up until r equal to RO, to the left and to the right, there is a horizontal velocity profile. A horizontal, so it's the same. So in this area, yeah, in this area, they have the same velocity. Yeah, for common Newtonian fluid, yeah, usually it will be like this. Yeah, yeah, with the maximum being in the center. Yeah, however, yeah, I can say, yeah, the center is the highest among here and here, but it's actually the same to this side, yeah, to this side, yeah, to this small area. Yeah, it's the same. Yeah, but compared to this side and this side, yeah, it's higher. Yes. Yeah, but there is a horizontal velocity profile in the middle. Yeah, from r equal to 0 to r equal to RO. Yeah. Now we call this area, yeah, a plug flow region. Yeah, a plug flow region where the velocity is the same at this radius. Okay. Now, okay, in the plug flow region, yeah, the tau 0, yeah, can be also calculated using equation 26. So I will go down here. Okay. Yeah, in the plug flow region, so it's where the velocity is the same. Yeah, the tau 0 can be calculated using this. Yeah. And the Vx, yeah, at r equal to RO can be calculated using this equation. Yeah. So the velocity at the plug flow region and the tau O in the plug flow region, yeah, can be calculated using these two equations. Yeah, velocity in the plug flow region, tau O in the plug flow region. Okay. Now, meanwhile, yeah, for velocity, yeah, outside the plug flow region, then you have to use this equation. Yeah. Okay. So if I go up again, yeah, velocity in this region use 26. It's only 27. Plug flow, velocity in this region use equation 25. Equation 27. Tau 0 use 26. Yeah. Now, the volumetric flow rates or Q. Yeah. We'll go down first. Now, oh, I want to know the volumetric flow rate for all radius. Yeah, can be determined using equation 29. Yeah, where TR is actually delta P times R equal to 2L. Yeah, TR. Okay. Okay, so we go to example 3. Yeah, okay. Yeah. We have a printing pigment solution with properties similar to those in table 2. Flowing in a 1 centimeter diameter pipe. So this is the D of the pipe, this is the L. And then this is the pressure driving force is the delta P, yeah, or PO per PL, yeah. The pressure drop between the two ends of the pipe. Yeah. Calculate the flow rate Q. So we will use equation 29 at the end. Okay, so from table 3.5-2, I will go up again. Yeah, here. The printing pigment, right? So the tau O is 0.4, the mu is 0.25 PAS. So I will go down again. Okay, I put here 0.4 is tau O, mu is 0.25. Okay, I put all the known variables here. And then, since in the equation of 29, yeah, I need tau O and tau R, and then delta P, and then R, mu, and L, then I have to find tau O. Oh, tau O is 0.4, okay. Yeah. And then, the Jankov, please try to find the RO region. Yeah, the RO. So he wants to know, yeah, up until which parts is plug flow region. So he tries to find RO. So he puts 0.4 here as tau O, and then tau O is actually equals to delta P times RO over 2L. Okay, delta P we know from the problem here. L we know from the problem also here. Then we can find RO. Is here. Okay, and then for tau R, yeah, for tau R, yeah, we also have to find tau R to fill in the equation 29, right? So tau R is equal to delta P times R, big R, capital R, over 2L. I put again all the known value here. Yeah, I know also the R value from this 1 centimeter over 2 centimeter. Yeah, so it's 5 centimeter, 5 centimeter. Sorry, 1/2 centimeter. I mean, 5 millimeter equals to 0.005. So this. So I know tau R as well. Then I will use equation 29. Okay, I put all the known value from equation 29. Yeah, then I can get Q, right? The volumetric flow. If I want to know the velocity, the average velocity, yeah, did they ask about the average velocity? Oh no. But it seems like Jankov wants to know the average velocity. Yeah, then they will use these equations Q over pi times R squared. So yeah, this. And then, oh yeah, sometimes we have to mix, yeah, the TIF. We have to agitate the TIF, yeah. So previously on subchapter 3.4, we talked about agitation and mixing for Newtonian fluid. Now we are talking about the agitation or mixing in non-Newtonian fluid. Yeah, so I will go down first here. Yeah, nah. Okay, so similar to previous subchapter, subchapter 3.4, agitation power, yeah, is obtained using the power number or NP. Yeah, as in equation 3.4-2. Yeah. Nah, meanwhile, NP, NP in this TIF, can be obtained using equation, using figure 6. Nah, this. Yeah. So if you still remember from equation from subchapter 3.4, yeah, when you get the n exon RE, yeah, then you can get the NP using the graph, right? With 6 curves, as long as I remember, yeah. After you get NP, then you can get P, right? So it's similar to what we have previously talked about. Yeah, in this subchapter, we will also use almost the same type of graph, but different one. Yeah, so figure 6 here. So we will obtain NP by using this figure 6. Yeah, after we know the NRE axon. N. Now, but as you can see, there's only one line here. Yeah, this one line represents the agitator type of flat 6-plate turbine with disc. Okay, and then the unREN axon here, yeah, the equation is this, yeah, or you can see equation 39 above. Yeah. Yeah. So once you know the NRE and xn, then you can find the NP using the figure down below. Yeah. Or sometimes, you can also use this NRE xn equation, for pseudoplastic fluid. So I can say that for general one, for all TIF fluids, you can use 39. But sometimes, for pseudoplastic fluids, you can also use equation 45. But please remember, since it's applicable only for pseudoplastic, the n value shall be less than 1. Miss, so if my n is higher than 1 or it's shear thickening fluid, then I cannot use this equation. Yes, you cannot use. You use equation 39. Okay? Now, this is a note, So for figure 6, for figure 6 below here, it's actually a profile obtained at an agitation system with 4 baffles, dA per W is 5, L per W is 5 to 4, dT per J is 10. So if these requirements are not met, if one of these requirements is not met, then you cannot use this figure. Okay. Now, okay, the flow pattern, of pseudoplastic fluids, the flow pattern of pseudoplastic fluids shows greater velocity gradient compared to the Newton's one. In agitation system. So sometimes, near the for, let's say like this, for Newtonian fluids, the fluid near the agitation system, it will be turbulent. If it's turbulent, then near the wall, maybe it's still turbulent, but lesser NRE. But for non-Newtonian fluid, since it has a greater velocity gradient, sometimes near the agitation is turbulent, but near the wall is laminar. Because of the high apparent viscosity. Okay. So if you have any questions, just drop me a message through the WhatsApp or through YouTube. Or you can just directly meet me in the class. Okay, thank you so much for contributing to this online class. So I will meet you next week on Monday, and then after that we will have we will study another chapter, which is chapter 14. Thank you so much and have a great weekend.